In September 1939, German Naval Command assessed the North Sea through tables, not through intuition. Patrol grids, minefields, tidal windows, hydrographic depth charts, endurance curves. Submarine U-47, a Type 7B boat with a surface displacement of 753 tons and a pressure hull rated to approximately 230 meters, was assigned an operational envelope that explicitly excluded Scapa flow. The anchorage was treated as a closed system. Multiple British anti-submarine barriers scuttled block ships at Kirk Sound and Scary Sound. Control channels narrowed to widths below 50 meters, tidal currents exceeding 8 knots during peak flow, and water depths fluctuating between 9 and 15 meters created a geometry hostile to a submarine with a 4.74-meter draft and a single pressure hull vulnerable to grounding. German command staff modeled this as a terminal constraint. If U-47 entered the area, it would not exit. This was not a judgment about courage. It was a calculation of hydrodynamics, navigation tolerance, and error margins measured in seconds. U-47 departed Kiel on October 8, 1939, under the command of Captain Lieutenant Gunther Preen, carrying 14 torpedoes, including G7 electric models with a nominal speed of 30 knots and a warhead mass of approximately 280 kilograms. The boat's endurance was defined by battery capacity and diesel fuel, not by ambition. At periscope depth, submerged speed above 4 knots began to collapse battery reserves exponentially. Inside the pressure hull, the margin for delay was counted in minutes. North of Scotland, weather conditions degraded celestial navigation. Cloud cover erased star fixes. Dead reckoning accumulated error. The technical anchor here was inertial drift. Each hour without a confirmed fix expanded positional uncertainty, tightening the corridor through which the submarine would later have to pass. British defenses at Scapa Flow were incomplete but not absent. The block ships sunk after the First World War had shifted under tidal stress. Gaps opened unpredictably. These gaps were not mapped with precision. They existed as variables. The Royal Navy compensated by relying on assumptions of denial rather than continuous detection. Fixed defenses replaced mobile patrol density. Hydrophone coverage was inconsistent due to seabed composition and acoustic clutter. This created a system optimized for surface threats and large-scale incursions, not for a single hull operating at minimum speed with engines shut down. The limiting factor was acoustic discrimination. At speeds below 2 knots, U-47's noise profile merged with ambient tidal flow, effectively collapsing the signal-to-noise ratio available to British listeners. On the night of October 13, 1939, U-47 approached Kirk Sound. The tide was flooding. This mattered more than visibility. A flooding tide reduced relative current against the submarine, allowing controlled drift rather than forced propulsion. Preen ordered engines stopped. The boat moved on residual momentum and current vector. The technical constraint was rudder authority. At speeds below 1 knot, hydrodynamic control surfaces lose effectiveness. Steering became a function of micro-adjustments and delayed response. A single overcorrection would yaw the hull, exposing it broadside to the current and pushing it into the block ship debris. The submarine passed within meters of grounded steel hulls, with clearance measured in tens of centimeters. The margin for error was smaller than the pressure hull plating thickness. Inside Scapa Flow, the anchorage appeared inactive. This was not because it was undefended, but because it was optimized for a different threat model. Battleships lay at anchor with minimal readiness. HMS Royal Oak, a Revenge-class battleship with a displacement exceeding 29,000 tons and a belt armor thickness up to 330 millimeters, was not expecting a submerged attacker inside the perimeter. Anti-torpedo nets were incomplete. Internal compartments were not at action stations. The ship's vulnerability was temporal. Readiness lagged threat arrival. U-47's presence exploited this delay, not through surprise alone, but through the collapse of response time to zero. At 0:58 on October 14, 1939, U-47 fired a salvo. Initial torpedoes malfunctioned. One detonated prematurely. Another failed to detonate. This was not unexpected. Early war German torpedo reliability was compromised by magnetic pistol failures and depth-keeping errors. The technical anchor here was feedback delay. Torpedo failure did not trigger immediate defensive action aboard Royal Oak because the detonations were misinterpreted as internal explosions or distant impacts. The absence of an immediate counter-response extended U-47's firing window beyond what British doctrine assumed possible. A second salvo was launched at 1:16. This time, torpedoes struck amidships. Flooding was rapid. Royal Oak capsized within minutes. More than 800 sailors were killed. U-47 did not remain to observe. Battery capacity, not tactical opportunity, dictated withdrawal. Remaining submerged inside the anchorage would increase the probability of detection as alarm states propagated. The submarine reversed its ingress route under ebbing tide conditions. Now the current opposed movement. Engines were again minimized to reduce acoustic signature, but propulsion was unavoidable. Each shaft rotation increased detectability. The limiting factor shifted from navigation to exposure time. German command, monitoring radio silence and expected patrol schedules, had already begun to classify U-47 as lost. The operational model did not include a successful exit vector. Statistical loss tables absorbed the boat before confirmation. This was not pessimism. It was systems logic. A submarine that violated multiple exclusion constraints was expected to be eliminated by at least one of them. Mines, patrols, grounding, detection. Survival required all failure modes to remain inactive simultaneously. Doctrine assumed this probability approached zero. U-47 surfaced in the North Sea days later. The system was wrong, not because the defenses were absent, but because they were configured around average behavior. U-47 operated at the edge of mechanical control, temporal coincidence, and human decision latency. The escape was not a breach of doctrine. It was an exposure of its assumptions. The event forced recalibration, not celebration. Subsequent British defenses would close the physical gaps with concrete causeways and Churchill barriers, replacing probabilistic denial with absolute obstruction. The physics of water would no longer be negotiable. The implications extended beyond Scapa flow. They propagated through Atlantic convoy doctrine, harbor defense engineering, and submarine command risk models. U-47 did not demonstrate that such operations were repeatable. It demonstrated that under specific hydrodynamic, acoustic, and temporal conditions, exclusion systems fail silently. That silence, measured in minutes and meters, was sufficient. The British response unfolded through engineering before rhetoric. Within hours, Admiralty assessments reframed the loss not as an isolated penetration, but as a system's failure rooted in geometry and flow. Scapa flow had been treated as a static enclosure. U-47 exposed it as a dynamic environment governed by tides, inertia, and time-dependent readiness. The anchorage's defensive architecture assumed that barriers were absolute once seen placed. In practice, they behaved as elastic constraints. Steel hulls shifted, silt migrated, channels evolved. The technical anchor that now dominated planning was closure certainty. Defenses would be redesigned to eliminate variability rather than manage it. Inside the Kriegsmarine, the episode was dissected with the same detachment. U-47's success did not validate aggressiveness as a doctrine. It validated boundary exploitation. Preen's navigation reduced propulsion to near zero, converting a powered vessel into a passive body moving within a current field. This inverted the usual relationship between submarine and environment. The sea was not resisted. It was used as a vector. The constraint was controllability at low speed. Below a threshold, the submarine ceased to behave as a ship and became a mass with delayed response. That transition point, where command inputs no longer yielded immediate motion, was where the operation either failed catastrophically or passed unnoticed. The window was narrow. The margin was unforgiving. British countermeasures accelerated. Temporary booms gave way to permanent causeways. Concrete barriers were designed to rest on the seabed, removing tidal undercutting as a variable. Depth contours were reshaped to deny submerged clearance entirely. This was not a tactical fix. It was a physical rewrite of the battle space. By constraining depth below a submarine's draft plus safety margin, planners removed discretion from the attacker. The limiting factor became simple: no water, no passage. Patrol density mattered less once geometry itself enforced denial. Yet the reverberations extended offshore. Harbor defense assumptions fed directly into convoy escort logic. If a submarine could appear where it was not supposed to exist, then the initial conditions of every engagement were suspect. Escort screens widened. Sonar watch cycles shortened. The technical anchor here was operator fatigue. Increased watch frequency reduced individual alertness over time, introducing a different vulnerability. Systems traded spatial certainty for temporal strain. Detection probability increased, but so did false negatives caused by exhaustion and noise saturation. For German command, the lesson hardened into operational filters. Penetration missions were treated as non-repeatable outliers unless environmental parameters aligned precisely. Tidal amplitude, moon phase, weather cover, and enemy readiness states were logged and cross-referenced. The success did not loosen constraints, it tightened them. Risk models were updated to reflect that survival hinged on synchronized failures across multiple enemy subsystems. Remove one coincidence and the probability collapsed. The anchor here was concurrence. Multiple independent conditions had to align within the same narrow time window. U-47's escape also altered internal British damage control doctrine. Royal Oak's loss demonstrated how readiness lag amplifies vulnerability. Compartments were not sealed. Counterflooding orders were delayed. The ship's stability margin vanished once longitudinal flooding exceeded design assumptions. Battleships at anchor were reclassified as transitional states rather than safe states. Readiness levels increased even in presumed sanctuaries. This imposed a continuous load on crews and machinery. Where accumulated, maintenance windows shrank. The constraint became sustainability. Permanent readiness eroded long-term effectiveness. In the Atlantic, these pressures converged. Submarines refined low-speed approaches, accepting reduced maneuverability in exchange for acoustic invisibility. Escorts improved active detection, but struggled with boundary conditions near harbors, shoals, and shipping lanes cluttered with civilian traffic. The sea itself imposed limits on certainty. Sound bent, currents carried, time-delayed responses. Each system compensated for one weakness by exposing another. U-47 did not redefine naval warfare through a single sinking. It revealed that defensive systems optimized for average threats fail at the extremes. At those extremes, physics dominates doctrine. Water depth, current velocity, battery discharge curves, and human reaction times form a closed equation. When variables align, outcomes appear improbable. When they misalign, the same attempt becomes fatal. German naval planners revisited the Scapa flow incident not to replicate it, but to bound it. The operational record showed that U-47 survived by remaining inside a corridor where propulsion, detection, and time interacted nonlinearly. The submarine's electric motors, rated for short-duration output, were used below their efficient range. Battery discharge curves at low load flattened, extending submerged endurance marginally but decisively. This created a narrow band where acoustic output dropped faster than energy consumption increased. Outside that band, endurance collapsed. Inside it, the boat existed longer than expected. The constraint was mathematical rather than tactical. Small deviations in speed produced disproportionate changes in detectability and remaining time. British intelligence, reconstructing the entry and exit paths, identified that the failure was not primarily sensor blindness, but decision latency. Hydrophone contacts that might have been ambiguous were not escalated, because escalation protocols assumed layered confirmation. A single weak signal did not justify action. The system required correlation. Correlation required time. U-47's transit time through the critical zone was shorter than the correlation window. This temporal mismatch neutralized the defensive process without disabling any component. The limiting factor was procedural inertia. The defenses functioned as designed, but their design assumed a longer exposure. As concrete barriers rose across the eastern approaches to Scapa flow, British engineers focused on load-bearing stability rather than rapid deployment. The Churchill barriers were dimensioned to resist tidal scour and storm surge, locking their bases into bedrock and compacted seabed. By removing underkeel clearance entirely, they eliminated the submerged threat vector. This shifted defensive philosophy from detection to exclusion. Detection systems could fail. Geometry could not. The constraint became absolute depth denial, independent of operator performance or alert state. In parallel, submarine commanders adjusted training. Low-speed handling drills emphasized delayed rudder response and the risk envelope of near-stall hydrodynamics. At speeds approaching zero, the submarine's turning circle expanded dramatically. Helm inputs lagged by seconds. Overcorrection risked broaching or grounding. These conditions were survivable only in predictable current fields. Random turbulence introduced uncontrollable yaw. The technical anchor here was flow uniformity. Without a stable current vector, passive movement became chaotic rather than concealed. The Royal Navy responded by increasing mobile patrol density outside fixed defenses. Destroyers and trawlers extended barrier lines seaward, attempting to intercept submarines before they reached confined waters. This created a trade-off. Increased patrol coverage diluted fuel and crew endurance. Patrol speeds, optimized for coverage, generated acoustic noise that masked contacts. Slower speeds improved listening but reduced area control. The system oscillated between these states. There was no stable optimum. Each adjustment exposed a different weakness. Within the Kriegsmarine, Scapa flow became a reference case for probabilistic success rather than a template. Penetration was logged as a function of tide tables, moon illumination percentages, and expected enemy readiness cycles. Deviations outside narrow tolerances downgraded mission feasibility. The escape did not relax caution. It hardened it. The constraint was repeatability. A success that could not be reliably reproduced was strategically marginal. It could shock but not sustain pressure. The psychological effect on British crews persisted beyond structural repairs. Anchored ships adopted higher readiness postures, maintaining closed watertight doors and active watches. This increased internal humidity, mechanical wear, and crew fatigue. Over weeks, these factors degraded habitability and maintenance standards. Readiness became a consumable resource. The more it was maintained, the faster it decayed. The limiting factor was endurance of the system as a whole, not of any single ship. In the Atlantic approaches, these lessons converged. Submarines exploited low-speed acoustic shadows near shipping lanes, while escorts relied increasingly on active sonar pulses that revealed their own positions. Each side adjusted parameters rather than strategies. Depth settings, speed thresholds, watch rotations. Warfare became iterative tuning under pressure. The environment imposed ceilings that neither side could exceed without incurring disproportionate loss. U-47's transit through Scapa flow thus remained singular not because it was miraculous, but because it occurred at the intersection of unclosed gaps, procedural delay, and physical thresholds. When those variables shifted, the window closed. Subsequent attempts would face barriers no longer subject to drift or interpretation. Concrete replaced assumption. Geometry replaced probability. The sea, momentarily permissive, was constrained again by mass and volume rather than vigilance. The recalibration did not stop at harbors. It propagated into fleet disposition and command doctrine on both sides. British naval planners began to reassess how much trust could be placed in assumed denial zones. Areas previously labeled secure were reclassified as conditional, their status dependent on tidal phase, traffic density, and readiness cycles rather than static charts. This reclassification altered fleet basing logic. Capital ships were redistributed, reducing concentration but increasing transit exposure. The technical anchor here was dispersion radius. By spreading assets to reduce single-point vulnerability, transit time increased, and with it exposure to open water submarine attack. Security traded one risk profile for another. German submarine command analyzed the escape phase with equal rigor. The exit from Scapa flow occurred under conditions of rising alert, but before the full activation of countermeasures. The delay between the first confirmed sinking and the establishment of a coordinated response was governed by communications latency. Reports moved through shore stations, command centers, and fleet units with inherent transmission delays. Orders required confirmation. Confirmation required repetition. This sequence consumed time measured in tens of minutes. U-47's egress exploited that interval. The constraint was not secrecy, but speed relative to the enemy's decision loop. Once the loop closed, survival probability would have collapsed. This insight fed into broader U-boat operational planning. Commanders were instructed to think in terms of decision cycle penetration rather than physical penetration alone. A submarine did not need to remain invisible indefinitely. It needed only to remain unclassified long enough to exit the engagement space. Acoustic contact without classification was functionally equivalent to no contact at all. The limiting factor became classification time. If the enemy could not decide what they were hearing quickly enough, the submarine retained freedom of movement. British escort forces responded by simplifying escalation protocols. Ambiguous contacts were more readily treated as hostile. This reduced classification time, but increased false positives. Escorts expended fuel and depth charges against noise. Equipment were accelerated. Crews operated under sustained tension. Over time, the rate of mechanical failure rose. Sonar sets drifted out of calibration. The constraint shifted to maintenance capacity. Aggressive response shortened reaction time, but eroded the material base required to sustain it. The engineering response at Scapa flow reached completion as the Churchill barriers sealed the eastern approaches. Their mass and placement transformed the anchorage into a fundamentally different system. Water flow patterns changed. Tidal exchange was reduced. Sedimentation increased. The harbor became quieter acoustically, but less forgiving to maneuvering errors. For surface ships, turning basins shrank. For submarines, the equation ended. There was no longer a submerged path to analyze. The defense no longer relied on vigilance or interpretation. It relied on the impossibility of passage. Yet the memory of the penetration lingered in training manuals and staff colleges. It was studied as a case where system assumptions failed under edge conditions, not because components were absent, but because their interaction created blind intervals. These intervals were short, but they were real. The technical anchor here was synchronization. Defensive layers activated sequentially rather than simultaneously. That sequencing created exploitable gaps, measured in minutes rather than miles. In the Atlantic, similar patterns emerged repeatedly. Convoy battles were decided less by individual attacks than by cumulative strain on detection and response systems. Submarines adjusted depth and speed to sit just below optimal sonar ranges. Escorts adjusted sweep patterns and listening schedules. Each side approached physical and human limits. Fatigue reduced reaction speed. Overuse degraded equipment. The environment amplified small errors. A contact missed by seconds could not be recovered. U-47's mission thus became a reference point for understanding how modern naval warfare behaved under constraint. It demonstrated that control was never absolute, only conditional. Systems worked until they reached thresholds where feedback lagged behind events. Beyond those thresholds, outcomes shifted rapidly and irreversibly. Once the window closed, it did not reopen. Future operations would unfold in a battle space reshaped by concrete, steel, and revised doctrine, where the margins that once allowed passage had been engineered out of existence. As the war expanded beyond confined waters, the Scapa flow penetration influenced how both navies interpreted uncertainty. British planners began to treat every delay in detection as a structural vulnerability rather than an operational lapse. Charts were revised to include not only depth and obstacles, but expected response times under varying alert states. Defensive zones were no longer defined solely by geography. They were defined by how long it took for information to move from sensor to command to action. The technical anchor was information transit time. Even perfect sensors were irrelevant if their output arrived too late to matter. This recalibration altered the deployment of early warning systems. Listening posts were repositioned closer to probable approach vectors, reducing acoustic range but shortening reporting delays. This sacrificed early detection for actionable detection. The window between contact and response narrowed, but the overall coverage shrank. Blind sectors emerged elsewhere. The sea did not allow uniform optimization. Every gain produced a compensating loss. The system became brittle at its edges. German U-boat command absorbed these changes unevenly. Some commanders adjusted by prioritizing speed over concealment during withdrawal, accepting brief exposure to shorten time inside hostile zones. Others doubled down on silence, trusting that reduced acoustic signature would keep them unclassified long enough to escape. Both approaches were bounded by the same constraint: battery depletion. Electric propulsion imposed a finite, submerged duration that could not be negotiated. Every tactical choice consumed the reserve differently. Speed spent energy quickly. Silence spent time. Neither could be extended indefinitely. In operational simulations, German analysts noted that the most dangerous phase of any penetration was not the attack itself, but the interval immediately after. Detection probability spiked once the enemy recognized a breach. Countermeasures multiplied. Search patterns overlapped. Random chance decreased. Survival curves steepened sharply. This phase was governed by convergence. As more units focused on a single contact, uncertainty collapsed. The technical anchor here was force concentration over time. Once sufficient assets converged, escape probability approached zero regardless of individual skill. British doctrine evolved to accelerate that convergence. Communication channels were streamlined. Authority to deploy countermeasures was pushed downward, reducing approval delays. This decentralization shortened reaction times, but increased the risk of uncoordinated action. Depth charges were released more readily, often without confirmed targets. Ammunition expenditure rose. Supply chain strained. The limiting factor became logistics throughput. Aggressive defense consumed material faster than it could be replaced, especially in remote patrol areas. At Scapa flow itself, the completed barriers reshaped daily operations. Tidal flow reduction altered salinity gradients and current speeds within the anchorage. Mooring practices were adjusted to account for reduced flushing. Sediment buildup required periodic dredging. These secondary effects were accepted costs. The primary requirement was denial certainty. Once achieved, other inefficiencies were tolerated. The defense was no longer flexible, but it was final. In the Atlantic theater, lessons from Scapa flow manifested in subtler ways. Convoys tightened spacing to reduce sonar shadow zones between ships. This improved collective detection, but increased collision risk in poor visibility. Navigation errors multiplied under blackout conditions. Again, geometry imposed trade-offs. Safety against one threat increased vulnerability to another. The technical anchor was spatial compression. Reduced spacing constrained maneuvering options, making evasive action slower and less effective once an attack was detected. Submarine commanders exploited these constraints by positioning themselves along predictable convoy tracks, minimizing maneuvering and conserving energy. Engagements became exercises in patience rather than aggression. The first torpedo launch often mattered less than the timing of withdrawal. A submarine that attacked too early extended its exposure. One that waited too long risked battery exhaustion. The balance point was narrow and shifted with sea state, escort density, and time of day. Over time, the singularity of U-47's mission hardened into a broader understanding. It was not remembered as a model to copy, but as a boundary condition that revealed where systems failed first. Harbor defenses became rigid. Convoy defenses became reactive. Submarine tactics oscillated between speed and silence. None of these elements operated in isolation. They interacted through delays, limits, and thresholds imposed by physics and human capacity. In that environment, outcomes were decided less by intent than by alignment. When current, depth, battery state, detection protocols, and decision cycles aligned within narrow tolerances, penetration or escape became possible. When one element fell out of alignment, failure followed rapidly. The war at sea settled into this pattern, governed by margins measured in meters, minutes, and remaining ampere-hours, with little room for correction once those margins were crossed. As these patterns stabilized, naval warfare began to resemble a continuous stress test rather than a sequence of discrete engagements. Systems were no longer judged by peak performance, but by how they behaved under sustained load. British escort forces operated on rotations that compressed rest cycles. Watch schedules shortened. Reaction speed initially improved, then degraded as fatigue accumulated. Sonar operators began to miss weak contacts not because equipment failed, but because perceptual thresholds shifted under constant noise exposure. The technical anchor here was sensory saturation. Beyond a certain density of stimuli, additional signals reduced clarity rather than enhancing it. German submarines faced a parallel constraint. Extended patrol durations increased mechanical wear on diesel engines and electric motors. Maintenance at sea was limited by access and spare parts. Small inefficiencies compounded. Fuel consumption rose slightly above nominal rates. Battery capacity decayed over repeated charge cycles. These losses were incremental but irreversible during a patrol. The constraint was degradation over time. A submarine that began an operation at full efficiency did not remain so. Every day at sea narrowed the margin for maneuver during critical phases. Command decisions increasingly accounted for these slow variables. Patrol areas were adjusted not only for shipping density, but for expected mechanical attrition. Boats nearing the end of their endurance were reassigned or recalled, reducing coverage in some sectors. This created temporal gaps in the patrol grid. Allied convoys occasionally passed through these gaps unchallenged, not because submarines were absent, but because their systems had reached operational limits. The sea imposed a rhythm that neither side could override. British analysts recognized similar rhythms in their own forces. Escort availability fluctuated with refit schedules and crew recovery periods. Attempts to maintain constant pressure led to diminishing returns. Ships spent more time in repair. Crews rotated out with cumulative fatigue injuries. The technical anchor here was sustainability of force generation. A fleet could surge temporarily, but it could not sustain peak output indefinitely without structural loss. These realizations fed back into doctrine. Both sides began to favor predictability over constant escalation. Patrol patterns stabilized. Escort tactics standardized. Innovation slowed as systems settled into equilibrium states defined by endurance rather than ingenuity. Scapa flow, once a shock, now appeared as an early signal of this dynamic. It showed how quickly a system could transition from assumed security to exposed vulnerability, and how the response to that exposure often introduced new constraints. At the operational level, the emphasis shifted toward managing margins. Submarine commanders tracked remaining battery charge with greater precision, planning attacks around minimum safe reserves. Escort commanders monitored fuel states and crew readiness, deciding when to disengage rather than pursue marginal contacts. Engagements ended not when one side was destroyed, but when limits were reached. The technical anchor was threshold management. Crossing a threshold triggered withdrawal as reliably as enemy action. In training and analysis, the language of certainty gradually disappeared. Reports spoke in probabilities and tolerances. Success was defined by staying within acceptable bounds rather than achieving decisive outcomes. This reflected the reality of a contested environment where absolute control was unattainable. The sea resisted simplification. It rewarded systems that recognized their own limits and punished those that ignored them. U-47's penetration of Scapa flow thus receded into context. It remained important not for its immediate effect, but for what it revealed about the structure of naval conflict under modern conditions. A single submarine exploited a convergence of delays, gaps, and physical thresholds. The response closed those gaps, but in doing so exposed others elsewhere. The cycle repeated, not as escalation, but as redistribution of risk. As the war progressed, this redistribution became the defining characteristic of maritime operations. Risk was never eliminated. It was shifted along the network of routes, bases, and patrol zones. Every solution carried a cost measured in time, material, or endurance. Those costs accumulated silently until they constrained future choices. In that sense, the legacy of Scapa flow was not the sinking itself, but the recognition that naval warfare had become a continuous negotiation with limits that could not be exceeded without consequence. The penetration of Scapa flow ultimately occupied a smaller place in the operational record than in memory. Its material effects were finite. One battleship lost, one harbor sealed, What endured was the recalibration it forced across naval warfare as a system. The event exposed that control at sea was never a static condition, but a balance maintained moment by moment against forces that eroded certainty continuously. Depth, time, energy, information, and human endurance interacted in ways that resisted permanent solutions. By late 1939, both sides had already begun to move away from assumptions inherited from the previous war. Fixed defenses were no longer trusted unless they removed physical possibility rather than merely reducing probability. Mobile defenses were no longer judged by coverage alone, but by how quickly they could concentrate effect. Submarine operations were no longer framed as sequences of bold actions, but as controlled passages through narrowing corridors of feasibility. The sea became less a battlefield than a medium that enforced limits impartially. Scapa flow demonstrated that systems fail first at their margins, not where forces are strongest, but where confidence replaces verification. The British anchorage was not undefended. It was defended according to an outdated threat envelope. German command did not gamble blindly. It calculated that under a narrow set of conditions, existing defenses would not synchronize in time. The outcome emerged from that misalignment. When alignment was restored through concrete, doctrine, and revised readiness, the window closed permanently. As the war expanded into the Atlantic, these lessons scaled outward. Convoys, patrol zones, and submarine hunting grounds became expressions of the same underlying logic. Each side sought to compress the enemy's decision space while preserving its own margins. Success was measured less by destruction than by forcing withdrawals, by exhausting endurance, by denying options. The decisive factor was rarely firepower alone. It was whether systems could operate long enough, fast enough, and with sufficient coherence under sustained strain. In that context, U-47's escape was neither an anomaly nor a template. It was an early data point in a conflict increasingly governed by thresholds. Once crossed, those thresholds triggered outcomes that could not be reversed. Batteries discharged past safe limits. Detection cycles closed. Forces converged. Fatigue accumulated beyond recovery. At sea, there was little room for correction after the fact. Decisions mattered most before they appeared dramatic. By the middle years of the war, naval operations reflected this understanding. Harbors were engineered to deny passage absolutely. Escort doctrines prioritized rapid classification and convergence. Submarine tactics balanced aggression against survival margins with increasing precision. The struggle became one of managing decline rather than achieving dominance. Every patrol, every convoy, every defense consumed resources that could not be fully restored. Seen in historical scale, Scapa flow marked the point where illusion gave way to structure. It revealed that the era of presumed sanctuaries was ending, replaced by a landscape where safety had to be engineered continuously and at cost. The sinking itself faded into statistics. The response reshaped practice. What remained was a clearer understanding that in modern naval warfare, victory did not belong to those who acted boldly, but to those who understood where the limits lay and arranged their systems so that the enemy reached those limits first.